For this problem, we're going to take 2 minus x plus sine of x and try to find one of its roots. It may have multiple, we don't know. But what we're going to do is we're going to pick a value that we think is going to be close to our solution and then go from there. Now, I'm going to be honest with you, when I first picked this out, I chose 1 as my starting value. And when I chose 1 and ran the algorithm, I got wild results. The numbers went all over the place. It failed to converge. So an important piece about Newton's method that you're going to have to watch out for is the sensitivity of the original guess. What I should have done is pick something closer to like 2 or something like that, but I didn't do that. So a happy compromise here is we're going to start with 1.85 and run the algorithm. Anyway, so we're going to fill out this table. Well, to fill out the table, we need to calculate the derivative. So f prime of x is -1 plus cosine of x. So what that tells me, if I had picked something like pi or 0 as my initial guess, I would have had an issue because that would be a critical value for f prime, and that would have caused this technique to fail. But luckily we didn't do that. So we have 1.85. We need to evaluate the original function at 1.85, and what you get there is 1.1113. And then we need to take the derivative at that point, which is -1.2756. And then we're going to take this value and divide it by that value, getting us -0.8712. And then finally, we're going to subtract this value from that value, getting us 2.7212. Now, once we've done that, we can take this value and we can run it into this function. So what we're going to do is we're just going to fill out the table here. We're going to say, all right, 2.7212. Now, realistically, our stopping condition is going to be when the inputs differ by this much. But another thing you end up doing in practice is you evaluate. And if you hit 0 on the head, you also can terminate there. But if I take 2.712 and I evaluate it, what I end up with is -0.3131. So notice we got a lot closer this time. And if we take its derivative, we get, so we take this and we plug it into that, we get -1.9129. And then if we divide this number by that number, we get 0.1637. And when we take this number, we subtract it from that number, we get 2.5575. So one thing that's probably helpful to note is that if this number is within this tolerance, you know that you're converging, because if you think about this minus that, this is really the difference between your old guess and your new guess, right? This minus that gets me this. So this is the difference between the new guess. Now, 2.5575, if we run that through the algorithm, it's going to produce the next time through. So if I do 3, blah, 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 it's going to get me 2.5542, which actually ends up being, if I run 2.5542 through the algorithm, I get 2.5542. So I ultimately get the same input there, and that's going to be the value where I check and say, okay, well, those no longer differ between 0.001, and that's really the algorithm in a nutshell.